Let's go over Chapter P, Day 3 notes. Okay, so to start off, some definitions here. Domain is the set of all values of x where a function is defined. And restrictions can vary depending on the function type. So for instance, for a rational function, you're going to be trying to look for restrictions in the denominator. For radicals, you're going to be looking for x values that will cause what's inside the radical to be less than 0. For trig functions, you're going to want to pay attention to where the vertical asymptotes are for certain types of trig functions. And so we'll look at some more examples trying to find domain. For range is a set of all values of y that have been mapped to the value of x in the domain of the function. And usually we'll have to look at the graph to determine the range, or we may need to know information about the parent graph and the corresponding transformation, usually to find out to really know what the range is for our graph. Okay, some transformation notes here. If I have a function in the form of a times f of bx plus c plus d, anything that is negative out front will indicate reflection over the x-axis. Any value that is being multiplied by the function, represented by a, will represent vertical stretch or compression. Any values that's being added or subtracted within the function is going to be indicative of the graph shifting left or right. And then any values outside is going to indicate that the graph is going to shift up or down. Okay, next up, composition of functions. And many times, not always, but many times we were going to have to determine the domain before simplifying. And so let's look at this instance. We have f of x being 3x squared. We have g of x being root x minus 2. So let's think about here we have a parabola, so our domain is all real numbers. Here, root x minus 2, our domain is going to be from 2 to infinity, this being a radical function. Determine f of g of x and the domain. So f of g of x means that we're going to plug g of x into the f of x function. And g of x is the root x minus 2. We plug it into the in for x, so we get 3 root x minus 2 quantity squared. So we want to be able to find the domain before we simplify. So the domain at this point will be 2 to infinity, and then when we simplify it, then the radical and the exponent will go away, leaving us with 3 times x minus 2. So make sure if we're doing composition, we want to determine our domain before we actually simplify. Because if we simplify and then we find the domain, then we miss out on the restriction that is part of our composition function. Okay, example 2, find g of f of x and then find the domain. So g of f of x, we're going to plug f of x being 3x squared. We're going to plug this in for the x of the g of x. So root 3x squared minus 2. So then to find the domain, we know that this expression cannot be less than 0. This expression has to be greater than 0. So we know we're looking for where 3x squared minus 2 is greater than 0. So just like how we handled inequalities, we're going to set up an equation, and we're going to solve for x, set up the sign line, and then test intervals within the sign line. So 3x squared is equal to 2. X is equal to plus or minus root 2 over 3. We're going to put those two values on the sign line, and then plug values into the original inequality to see if it's a positive or negative. So if I plug in a large negative value, that's going to convert to be a positive, and that's going to give us a positive value, this expression, so positive. In this region, if I plug in 0, 0 minus 2 is negative 2, which is less than 0, so we know that's negative. And then this portion again will give us positive value. Now we're looking for positive values. We're looking for where 3x squared minus 2 is greater than 0, so that we can ensure that this expression is a positive value. We cannot have a negative value inside the radical. So then that's going to give us these two regions. So we know our domain will be from negative infinity to negative root 2 over 3 union root 2 over 3 to positive infinity. And we have open circles here because we have inequality here being just greater than and not greater than or equal to. Okay, let's continue with notes. Test for symmetry for even and odd functions. So even function where we're going to have symmetry about the y-axis. We know that we're going to get symmetry about the y-axis algebraically if we can show that this is true. If we can replace every x with negative x, and then if we simplify it, and if we get the exact same as the original function, then we know we're going to get symmetry about the y-axis, or an even function. For an odd function, we're going to replace every x with negative x, and we're going to compare that with taking a negative and distributing it through the original function. If these two match up, then we know we're going to have symmetry about the origin. So example here of that. Then we're going to test symmetry for x squared minus 5, and we're going to test symmetry for x minus 2x cubed. X squared minus 5, we see that if we replace every x with negative x, this will go back to being a positive x squared and then minus 5. So if we replace every x with negative x, we're going to end up with the exact same equation as the original. So we know that this is an even function because f of negative x is equal to f of x. Okay, next up, x minus 2x cubed. We know that this won't be an even function because if I replace x with negative x, the negative will retain. The negative will still be there. It will not cancel out because we have odd power. But if I replace each x with negative x, we can test to see if this is an odd function. So negative x minus 2 times negative x cubed. And so this will reduce to be negative x plus 2x cubed. Now, to see if this is an odd function, we're going to compare this with distributing a negative through the original function. So I distribute negative through, I'll get negative x plus 2x cubed. And if we do that, we see that this will match up with f of negative x. So since f of negative x is equal to negative f of x, we know that we're going to get an odd function. So or symmetry about the origin. Okay, let's talk about piecewise functions. Let's graph our piecewise function, 1 minus x, where x is less than 1, and then root x minus 1, where x is greater than or equal to 1. And we are to discuss the domain and range. But first, let's see if we can graph. With piecewise functions, what I like to do is I like to create t-charts for both piecewise functions. So y equals 1 minus x, I have a t-chart here. And then y equals root x minus 1, I have a t-chart here. Now, the x values that I'm going to be choosing is going to be dependent on the restrictions that is provided for us. So x is less than 1. Now, we always want to start with the value that the restriction gives us, regardless of whether it is less than or greater than or equal to. So the tendency for students is that they want to start off with something like 0. But we do want to include 1s, but because even though 1 doesn't exist for this graph, the graph does get as close to 1 as possible, so we can put an open circle at 1. So we do want to start at 1. Okay, so I'm going to start at 1. And we want to choose values that is less than 1. So we know that the graph is going to start at 1 and it's going to exist to the left of 1. So I'm going to choose values less than 1, so I'll choose 0 and negative 1. Now the inequality here is less than, so we'll put an open circle. And we know that the graph is going to continue to negative infinity, so it's going to continue towards a negative direction, so I'll put an arrow indicating that. So we know that our graph will have an open circle on one end and then it'll have an arrow on the other. So from here I'm just going to plug these x values into my first piecewise function to determine the y values. So if I plug in 1, I'll get 0. If I plug in 0, I'll get negative 1. If I plug in negative 1, I'll get a positive 2. So then now I have my graph here, so 1, 0. and then I have 0, 1, and then I have negative 1, 2. Here, this is starts off with an open circle, so that is the first piecewise function. The second one, x minus 1, is greater than or equal to 1. So again, we're going to start at 1, but now I'm going to put a closed circle here to indicate that we are going to fill that in. So, but now we're going to go in the positive direction. X is greater than or equal to 1, so I'll choose 2 and 3, so on and so forth. If I plug 2 into the radical, I'll get 1. If I plug 3 into the radical, I'll get 3 minus 2, which is 3 minus 1, which is 2, so root 2. So here are the ordered pairs that will create my radical function. And 1, 0 does match up with this 1, 0 here, so the closed circle is going to overlap the open circle. So this will end up being a continuous function because the closed circle is going to fill in for the open circle. Now, if we look at the result of this piecewise function, we see that the domain is going to be all real numbers. There's not going to be any breaks, and the graph is going to continually extend to the left as well as to the right, to negative infinity as well as to positive infinity. So we have a domain here for all real numbers. The range are the y values from the lowest y value to the highest y value. So we see the lowest y value is going to be at the x-axis, so at 0. Now the graph is touching 0, so we do want to put a bracket there, and it's going to go up to positive infinity, so we'll put a parentheses there. So the range is from 0 to infinity. All right, finally, absolute value functions. Absolute value functions, y equals root x, for instance, y equals absolute value of x, can be rewritten as piecewise function always. Okay, so what we can do is we're going to take this function and we're going to write it as two linear functions. Okay, so piecewise absolute value functions always has the shape of v, either right side up or upside down, but it's always the combination of two linear graphs put together. So the first piecewise function is going to be the original x that you see here, the original term inside the absolute value, where x is greater than or equal to greater than 0. And the way we determine the restriction here is we're going to set the value inside the absolute value equal to 0. And then the other is going to be the negative version of the expression inside the absolute value. And then we're going to have the inequality going in the other direction. So here we have y equals root x, y equals x, where x is greater than 0 or to the right of x. And then here we have y equals negative x with a negative slope existing to the left of 0. Okay, next example here. We want to graph y equals absolute value of 2x plus 6, and we also want to rewrite it as a piecewise function. So first off, we know that the piecewise functions are going to be the original 2x plus 6, as well as the negative version of this, negative 2x plus 6. And the way we find the restriction, we're going to set the expression inside the absolute value equal to 0. So 2x plus 6 equals 0. Solve for x, we get 2x equals negative 6, so x equals negative 3. So 2x plus 6 will exist to the right of negative 3, and then negative 2x plus 6 will exist to the left of negative 3. So then we have the graph that looks like this. And the vertex is always going to be the expression inside followed by whatever is outside. Now here there's no values outside, so our vertex will simply be negative 3, 0, as we can see here in the graph.